In this lesson, there are actually two lessons on Chapter 10, Section 7. This one in particular follows the books, examples, and formulas for growth and decay. And we will be finishing out Algebra 2 State Standard number 12. If you followed along, we've already taken care of learning fractional exponents. We've already done exponential functions and graphed them. And today we need to focus our attention on growth and decay. So our objectives for today, we're going to use exponential logarithmic functions to solve growth and decay problems. Now, in particular, the kind of growth and decay problems we're going to focus our attention on in this lesson is a doubling growth formula. So when your population of size n is your initial amount, let's take a look at the formula. I'm going to use a lowercase n here. The textbook uses capital N subscript 0. I'm going to use a lowercase n because this is what we're starting with. This is our initial amount, and when things grow, we're going to end up with a larger amount, so I'm using a capital N to represent the larger amount. That way I think it makes sense in your understanding that we're starting out with less and we're ending with more in a growth formula. Alright, this particular growth formula is dedicated for growth that doubles. So that's a big old multiplication sign. Our initial amount times 2 because it's doubling. And then D represents the days, years, hours, or whatever unit of time we're doing that it takes for it to double. And then N is the final population, how much is left, or the final amount. And then T is how long we're letting everything grow in this particular regard. So let's take a look at an example or two and see how this goes. Let's start with our first one, which says a certain bacteria population doubles. That's important because that means we use this formula. Doubles in size every 12 hours. If we start with 2 bacteria, how many bacteria will we have after 2 days? Now, be careful as you read the problem because you want to make sure the unit of time is the same. They're saying it doubles every 12 hours, but they're asking us for days. So I've supplied in parentheses that we need to convert those 2 days into 48 hours. Alright, so let's take a look at what goes where in the formula. So there's the formula again. 2 is always staying there because it doubles. N is our initial amount, so we're starting with 2 bacteria. Lowercase n will be 2. And then T, we're going to let it grow for 48 hours. And then D is how long it takes to double, which it says it takes 12 hours to double. So when we substitute all the numbers into the formula, our final amount, capital N, equals our initial amount, 2, times 2 to the 48 over 12 power. And if we go ahead and simplify that, 48 divided by 12 is 4. Let's continue to simplify. 2 to the 4th power times 2 to the 1st power is 2 to the 5th power. And 2 times itself 5 times is 32. So after 48 hours, we will take those original 2 bacteria and they will now have multiplied to be 32 bacteria. Alright, in our next example, again, we have the same kind of bacteria that doubles every 12 hours, and they want to know by how much will it grow in those 2 days or 48-hour period. So we can see here we went from 2 to 32, and 32 is 16 times more than 2. Let's see if that's true in general. So we start with our formula. Final amount equals the initial amount times 2 to the 48 hours, how long we're letting it grow, divided by 12 hours, how long it takes to double. And we continue to simplify this. 48 divided by 12 is still 4. 2 to the 4th power is 16. So yes, no matter what our original amount is, our final amount is going to be 16 times that amount. In the previous example, we started with 2 bacteria. Our final amount was 32 bacteria, which is 16 times more. Alright, so it grows by a factor of 16 in a 2-day period. Let's look at our next formula for today, which is a half-life formula. It's kind of the opposite of doubling growth. And that's formula, let's post that up here while we've got it. The textbook uses capital N and capital N subscript 0. I like to use capital N for the initial amount and lowercase n for the final amount. And in this case, you'll notice that the sides are switched because we've got a decay problem. So our initial amount is larger, our final amount is going to end up smaller. And that's why I have them reversed in the doubling. So n, if is our initial amount we're starting with, has a half-life of h, so that's our measure of time, how long it takes for half of that material to be left. And then t is the amount of time we let it decay, and then 1/2 is 1/2. Capital N is our initial amount, what we're starting with. Lowercase n is our final amount, how much is left after it decays. So in this example, half-life of carbon-14 is 5,730 years. How much of 10 milligram sample remains after 4,500 years? Well, we'll start with the formula again, my variation of the book's formula using uppercase n and lowercase n. We're going to start with more, end with less. It's a half-life formula. T, how long we're letting it decay. H, how long it takes for half of it to remain. So as we substitute that in, capital N is 10, what we're starting with. A half is a half. We've seen it decay over 4,500 years, although I'm not nearly old enough to watch it that long. And it would take 5,730 years for half of it to be left. Right, we're going to have to do a little division, so mentally just imagine yourself using your calculator. 4,500 divided by 5,730. Round our calculator to 4 decimal place accuracy as we've established in this chapter. So that's 0.7853. And then we want to take 1/2 and raise it to the 0.7853 power. Doing that gives us 0.5802. Now if you don't remember this, remember we've got that any base to any power button. And for 1/2, I'm going to type in 0.5, raise it to whatever power. In this case, it was 0.7853, so 0.7853. And then find out that that is 0.5802. And if we round that to 4 places, that's plenty. All right, last thing we have to do is take 0.5802, multiply by 10. No calculator necessary for that. Multiplying by 10 just takes the decimal and slides it to the right one place. So we are left with 5.802 milligrams after 4,500 years, starting with 10. Right, and that seems to make reasonable sense. So let's continue on with another thought. Now, some of you are saying, well, why are we looking at these particular problems in the logarithm chapter? So far, these examples haven't required logarithms, and I agree with you in that. So let's take this same problem, and it could be solved using logarithms. What we're going to start with is the log of lowercase n. Unfortunately, I typed it in as a capital over here, so don't be confused by that. I'm going to take this equation, take the log of both sides. So the log of n is the log of 10 times 1/2 to that power, but then I've already done one step in my head. Remember, a log of any number raised to a power is the power times that log of number. And when you get the log of a product, which it's 10 times 1/2 to this exponent, it's the sum. So I've already done a couple steps in my head. And the log of 10, base 10, as you recall from this chapter, is 1. Log of 0.5 is negative 3.3010. And we're going to multiply that by, which is 4,500 divided by 5730, which is 0.7853. Multiply those two together, we get 0.7636 when we add that to the 1. And then we've got to solve this. Remember, that's going to be 10 to the 0.7636 power equals the number we wish. And that turns out to be 5.80. I didn't go to the same precision on that particular one. That's why the answer differs a little bit. But let me remind you, so if we're doing that, we're going to type in, again, your calculator, you might have to type the function first. You might have to type the number in first. This particular calculator requires the number first. So 0.7636. And then I'm going to do that inverse log button. So I need my inverse log. That's 5.802 as we've already established. So you could use logs to solve this particular problem, but the formula for half-life is set up easy enough that we don't need logs, depending on what we're solving for in this particular step. All right, we're going to segue into another formula, but before I get to the third formula for today, I'm going to remind you of a formula that you learned in elementary school. So in your previous math classes, you learned about interest. And the simple interest formula was interest you receive equals the principal, the amount of money you invest, times the rate, the interest rate. If it's 5%, 3%, 1%, that needs to be written as a decimal, times the time. And then the final amount of money you have would be the principal you already invested plus the interest that you got returned to you. Okay, so I is the interest, P is the principal, T is the time, usually in years, and then A in this formula is the final amount. So we're going to do a reminder example from our elementary school or previous math class days, just so we can segue into our new formula for today. So $1,000 is invested at 3% for 5 years. How much interest was earned? What's the total amount of money that you have? So 2 questions we need to answer. Interest equals principal times rate times time. The principal was $1,000. 3%, remember percent means out of 100 or divided by 100. So 3 divided by 100 is 0.03. That's the tens place, hundreds place, so that's 3 100s. And then for 5 years, T is 5. Very simply, if you take your calculator and multiply them, 1,000 times 0.03 times 5 gives you $150. So then, what's our total amount of money? Well, it's the principal we invested plus our interest. So our 1,000 plus the $150 that we got as the return on our investment. Total amount is $1,150. The interest was $150. Alright, so that's just a reminder, kind of a transference of learning from something you already knew to something that is new. And this particular interest formula is called compound interests. P is still the principal. R is still the interest rate. It's expressed as a decimal. T is still the time, typically expressed in years. A would be the final amount. What's different here about compound interest is N represents how many times a year that interest is compounded or calculated. So if N is 4 when we say the interest is compounded quarterly. Quarterly means 4 times a year. Monthly N would be 12. Daily N would be 365. Okay, so whatever it is, we need to pay attention to that in the problem. Here's our formula. The final amount of money equals the principal, the initial amount. So pretty much this is just like growth and decay. It's a growth problem. We're hopefully making money when we invest it. So P is my initial amount, A is my final amount. Just used in banking terms, P is the principal, A is my final amount of money. 1 is 1 plus R, the interest rate, divided by the number of times it's calculated, and all of that in the parentheses is raised to the nt power. Now, since this formula calculates the final amount, if you were interested in the interest, you would have to subtract the principal from your final amount to find out what the interest was. So let's take a look at an example of doing compound interest. How long would it take for an investment of $1,000 to triple in value if it's invested at a rate of 12% compounded quarterly? First of all, an editorial comment. If you can get a return on your investment at 12%, please take it. In today's economy, that's not something that you see. Right, well, $1,000 is how much we're investing, so that's our principal. Triple, well, we want the final amount to be 3 times 1,000 or 3,000. Rate is 12%, but remember that's going to be written as a decimal, so let's go back. P is 1,000, A is 3,000. Interest rate 12%, written as a decimal. Percent means out of 100 or divided by 100 is 0.12. And compounded quarterly, 4 times a year. So we will substitute those numbers into the formula. 3,000 equals 1,000 times 1 plus 0.12 over 4 raised to the 4t power. Alright, easiest thing to do to solve this problem, the very first step would be to take our initial amount, 1,000, divide both sides of the equation by that, because that'll simplify matters, and we will just have 3 equals what's in the parentheses here. 0.12 divided by 4 is 0.03. Add that to 1 is 1.03, raised to the 4t power. Now we know from previously in this chapter that if our variable is in the exponent, There's only one way to get it out of the exponent, and that's using logs. So we're going to take the log of both sides of this equation. The log of 3 equals the log of 1.03 to the 4t power. Because we remember that when you have the log of a number raised to a power, one of our three properties of logs says that's the same as the power times the log of the number. Now that the variable is removed from the exponent, we'll be able to solve this. So let's try to isolate t to get it by itself. To do that, it's being multiplied by 4. It's also being multiplied by the log of 1.03. So I'm going to divide both sides of this equation by 4 and by 1.03. Multiply both sides. And I'm going to switch sides of the equation. So what was on the right, the 4's divide out, the logs of 1.03 divide out, all that's left is t. And I'm going to write that on the left, since we mostly like to see our variable on the left side of an equation. Alright, and that's going to be equal to whatever the log of 3 is, divided by whatever 4 times the log of 1.03. So we're going to need the log buttons on our calculator pretty soon. So remember, your calculator, you might have to type the 3 first, the log button second, or some of your calculators, the log button first, and the 3 next. In any event, we're going to do that and round our answer to 4 places, 0.4771. The log of 1.03, same thing. We're going to either press the log button first or type in the numbers first and then press the button. Log of 1.03 is 0.0128, and we'll have to multiply that by 4. 4 times 0.0128 is 0.0512. And again, I hope you're clearing out your calculator at every step of the problem, because as we go, we want to round each step of the problem to 4 decimal places. So now, when we divide 0.4771, type that in your calculator again, divided by 0.0512, that gives us approximately 9.3 years. And in this case, I don't think we need to round that to 4 places. 9.3, 9 3/10 of a year is close enough for accuracy. So you notice I changed my equal sign to my approximately equal sign. So again, to answer the question, if you've got $1,000, you find some place that will compound it 4 times a year at 12%, how long will it take to get $3,000? Answer to that question is 9.3 years. And that pretty much concludes this lecture, this lesson. It is important, though, and crucial that you memorize these formulas. They are found on my website on the formula sheet for Chapter 10. So it's important because without the formula, once again, you will not be able to solve the problem. And as the knowledge iceberg points out, memorizing the formula is not enough. Knowing what goes where is crucial. So for growth, we're starting out with a small amount, ending up with a larger amount, how long we are letting it double, and how long it takes it double. That's what everything represents in the formula. For a half-life formula, again, we're starting with our initial amount, which is larger because things are decaying. Our final amount is smaller. How long we're letting it decay in the numerator, and how long it takes to decay to half of the original amount in the denominator of that exponent. And then the new third formula for today is compound interest. Once again, our initial amount, which we call principal, and our final amount. Initial amount times 1 plus the interest rate expressed as a decimal over n, all raised to the nt power. So if we'll do a little check for understanding in class, and you should probably do one now, but that concludes today's lesson.